This is our first DSS of the term. I'm Professor Buriba in Civil Environmental Engineering. And it is my delight to welcome you to our first DSS, so Chiang Mai Distinguished Speaker Series lecture of the term. And I want to give you just a bit of an overview of the various lectures that are coming this term. We're going to have a series of 4 fantastic speakers. The first one today, Professor Synolakis, Professor Gadgil, Professor Kretschmar, and Professor Delgado, spanning a range of domains from tsunami hydrodynamics, water treatment, biochemistry in the environment, and soft matter and statistical physics. Today we have a special DSS. As our first guest of the term is Professor Synolakis, who did seminal work in tsunami prediction and who will be introduced by our very own Professor Chiang Mai, in whom the series is dedicated. And so my job today, contrary to usual, is to actually introduce Professor Chiang Mai. And so I'll therefore take this special time to have this special introduction. So Professor Chiang Mai is Ford Professor of Engineering and Emeritus Professor in the Department of Civil Environmental Engineering. Professor Mai did spectacular work in a very diverse range of fluid mechanics and mechanics domains, from theoretical hydrodynamics, ocean and coastal waves, fluid-solid interactions, poroelasticity, sediment transport, and wind-waves interaction, important for remote sensing data. To cite a few. In particular, his analytical work on wave diffraction and refraction by large bodies has been applied to wave forces and motion of offshore structures. Professor Mai is also an outstanding teacher and author of numerous seminal contributions on mathematical analysis in engineering, ocean surface waves, nonlinear dynamics, and multiscale mechanics. And in testimony of his achievement, Professor Mai is a member of the National Academy of Engineering, and he had received many awards for his spectacular contributions in waves and fluid mechanics, including the Theodor von Kermel Medal in 2007, the Moffat-Nicol Award in 1992, the International Coastal Engineering Award from the American Society of Civil Engineering for outstanding research and teaching contribution to coastal engineering and theoretical fluid dynamics of sea waves. So without further ado, please join me in welcoming our very own Professor Chiang Mai and our speaker of the day, Professor Synolakis.
Thank you. Thank you, Lydia, for in the introduction of the non-speaker. It's my great pleasure and honor to introduce today's speaker, Professor Costas Synolakis. Professor Synolakis is one of the top experts in the science of tsunami, natural hazard that has disastrous in past decades. He is the founding director of Tsunami Center at the University of Southern California. As in that position, he not only does tsunami research, but he advises tsunami warning system planning and installation worldwide. And when he has time, he is an excellent communicator of tsunami science to the general public. And after every major tsunami event, he is always sought after by major media, such as New York Times, Nature, Wall Street Journal even, and science magazines and so forth. And one of his outstanding activities includes being a team member of an international team that inspects Indonesia right after the 2004 Indian Ocean tsunami. Just 1 week after, he flew to Indonesia to inspect the damages and so forth. And his activities includes not only tsunami, but many other aspects of fluid mechanics, which I don't want to list anymore. Last night, I did not watch TV for the Oscar. Instead, I watched Professor Synolakis on YouTube for his TED Talk in Athens, Greece. That was, of course, given in Greek. I hope today we'll enjoy his lecture given in English.
Okay. Thank you very much, Professor Mai. I don't need it. Good afternoon. It gives me great pleasure, and it's a great honor to be here at MIT, where Professor May, Oli Madsen, and their students did the seminal contributions in the study of tsunamis. So I will discuss, from my perspective, where we stand. And very, very briefly, tsunami science is punctuated, just like the study of any natural hazard, by big catastrophic events. And looking back in the last 20 years, obviously the two big events that we've had is the Sumatra, the great Boxing Day earthquake of 2004 that killed the tsunami killed 280,000 people, and then the Japan tsunami of 2011. And I've put here, and just as a way of introduction, obviously what I will do is concentrate on over here, but where the progress that was made in 2005 to 2011, 2006 was my last seminar here at MIT, so I spoke about a few of these things. But back then, we really, starting in 2005, we start having real-time warnings. But these real-time warnings are not informed. We don't really have hydrodynamic computations per se, particularly inundation computations. You see, what is the problem in tsunami hydrodynamics other than basic science? The real problem that we have is actually making an accurate, targeted prediction of what the impact of the wave is going to be on any coastline long before the wave actually arrives, so that we're able to evacuate people. That is the grand challenge. Since 2005, we can actually do that, and we can use, in some cases, inundation computations. What we found out, tsunamis propagate on dry land faster than they do when they sow. We found out that geophysical scaling loss break, and I will refer to it briefly because this is what makes our work a little bit more challenging. And also counterintuitive observations that we get in the field, that if you have, for example, an island that is fronting a coastline, most people would expect that this island will shelter the coastline behind them. It turns out that the island enhances the wave run-up and the impact of the wave behind it. Since 2011, what we have learned was basically we can do hydrodynamic inversions, and I will explain what this means. Up to now, or at least up to 2004, and beginning from then slowly, we're converging towards merging seismic data with hydrodynamic data and producing better forecasts. Why merge them? Because the seismic data, which we use in hydrodynamics, the problem in hydrodynamics is we need the initial condition to make a prediction of the tsunami propagation. The seismic data are not sufficient, so we need to do hydrodynamic inversions and use some of the hydrodynamic data as the wave evolves, assimilate data in the computation. This is now possible. Tsunamis can generate large, coherent, turbulent, coherent structures. I will talk about this. Over long propagation distances, tsunamis, the leading wave of the tsunami is no longer, may not be, the largest wave in the tsunami wave train. One of the problems that we have faced over the years, and I've done a lot of field work, I've been about 25 tsunami surveys, and I've spoken to a lot of eyewitnesses, and sometimes they tell you it's the first wave, which wave is the largest, the second, the third. All of this varies, and we try to make some sense out of it, so I will talk about this. And then tsunami hazard analysis needs to include all possible scenarios, and of course, it's Fukushima that's there. So I'll talk in my talk about all these things on the right. Before I proceed, I want to actually acknowledge two people that never knew each other. On the right is Fred Reichlin, who's my PhD advisor, actually a student of Arthur T. Ippen here at MIT. The gentleman on the left is Professor Nick Ambrasis, Professor of Earthquake Engineering at Imperial College. He held the chair in Earth Sciences in the Academy of Athens, which I now have. Both of them, these two men, I think they met once in their lives. They hardly knew each other, but they both had the same perspective about natural hazards. And this is that, and they kept saying it in totally different contexts, but they were both, it's amazing how their views converged, that if you think, you always design for the worst possible scenario, and always remember that the worst may not have happened in the past. You see, humans, we have a fairly short time span. I mean, it's a fairly short time span on Earth. We are not necessarily aware of the cycles of the geological cycles, and a lot of times we might be tempted to think that we know about the worst that can happen. Both advocated the same thing. They used to tell me in different contexts, remember, you may not have seen the worst. And again, consequences of not seeing the worst. I mean, you see it, I mean, the sinking Seagull, the Korean ferry, the search for Malaysian 370. But let's go now into actual hydrodynamics. And I will explain briefly why the problem with this seismic inversion, is complex, and the assignment of the initial condition is very challenging. I will show you here a video, actually from the 1946 tsunami hitting Hilo, Hawaii. This, by the way, is the only film we had as a community, pretty much for 40 years, up until 1983, when there were some films about the tsunami in Japan. Believe it or not, these are pictures from Hilo, the tsunami hitting Hilo. Why this was, why this is important is that this triggered essentially the era of the warning centers. And one question that I always think about, can we predict the impact of such an event if it happened today? And the answer is yes and no. With the technology that we have, we still will have a hard time actually predicting what happened. It turns out that the earthquake in Unimac was a very special earthquake. It was what seismologists referred to as a slow earthquake. The size of the earthquake was a magnitude 7.5. An earthquake like this happens somewhere around the Earth pretty much about once a month. So it's not a very big earthquake. So, but yet it triggers a tsunami that goes in and kills 168 people in Hilo, Hawaii, goes all the way to French Polynesia. There are some reports that it even destroyed the little hut in Antarctica. How can, what's called a slow earthquake is an earthquake that reduces disproportionately large energy compared to the conventional earthquake size. And this is something that we still don't know how to differentiate between regular and these special earthquakes. And the other feature of this earthquake was that it triggered a co-seismic landslide. For those of you who are not actually in tsunamis, just to see what the impact was locally, what you see here is a lighthouse in Scott's Cap. This is about a year before the tsunami. It's gone. And here, I went on a field survey with George Plafker and Emil Lokal. The three of us, we basically hiked out there, and we traced essentially the WAC line, the debris line, from the 1946 tsunami. It was still there. Gives you an idea how far the wave penetrated. So this particular event, if an earthquake were to happen there today, based on seismic information alone, exactly because it is so complex. You have an associated co-seismic landslide. It's a slow earthquake. We wouldn't be able to actually predict its impact. So what is a warning center to do? Before I go into is actually to make a realistic prediction. One of the things that we need, again, to understand my work, you have to understand that a great part goes into defining the initial condition. And earthquakes, there are what geophysicists refer to as scaling laws. This means that you have an earthquake, the bigger the earthquake, the bigger the rupture area, the bigger the slip is. This is kind of intuitive. The question is how big? And this is needed because this is really what helps you define the initial condition, which is something that seismologists and geologists don't necessarily care about. For them, they give you information as to the size of the earthquake and the energy released. But for us, the details of the initial condition are extremely important. And scaling laws of this sort, one of the things that you will see is that for the very large events, which means for the seismic moment M0 is a measure of the earthquake energy. After about 30, which means a magnitude 8.8 event, you have very little data. So we really do not know how these parameters scale. So again, it's not extremely easy for us to define the initial condition because we need the simple parameters, the deformation area and the slip and the length of the deformation area. Another further difficulty in having the initial condition is the fact that the way that seismologists and geologists define the conventional earthquake magnitudes, this saturate. What you see here is for the different magnitudes, and so far, up until the 2004 tsunami, they relied very much on the surface waves, which is this MS magnitude. But you see here for mega earthquakes, a lot of the energy is in fairly long periods, 1,000 seconds or more, sometimes up to 10,000 seconds. What this means is that it will take a long time to actually sample an earthquake motion to be able to infer the correct earthquake size. So the answer is actually try to do a hydrodynamic inversion, which means use some of the measurements that it's now possible to get from deep ocean buoys that measure the change in the water depth, and use that information to augment the seismic information and infer a source, and from that, make a prediction. What you see here, beginning in 2004, is the 36 different predictions done by NOAA for different events. This was, I was telling you, that this is the problem, at least in deep water, of estimating the earthquake, the tsunami. We're well on the way of solving it. What you see here is what we call the energy diagram. This is the Japan tsunami. So, just to give you an idea, this is Chile 2014. So this is Chile 2010. And these are different minor events. For all these events, the inversion took place, and I'm not going to give you the details about this, but it's a fairly simple and straightforward hydrodynamic inversion where we have some pre-computed scenarios, and then we use them to be able, depending, and assimilate, as the tsunami arrives in different locations, assimilate this information. So at least in the deep water, we're doing okay. And if you look, you try to do, look more carefully in terms of, this is, again, Japan 2011. These are different locations across the Pacific, and you can see the different locations. This is, sometimes doesn't. If you look at all these points here, this corresponds to this wave time histories. This inversion that's done on the basis of only 2 measurements in the deep water. And you can see overall, it's fairly satisfactory. There are a couple of things here and there, but just on the basis of 2 records, and along with the timing, the seismic information, in the far field, this is all in the far field. In my talk, I will refer to far field and near field. Far field means fairly, far away, usually of the order of one source length. If you're more than 1 source length away, generally in tsunami hydrodynamics, we consider that, being the far field. So we're doing fairly well in the far field, and this is in the near field. And I promise, I'm going to show you a lot of wiggles that agree with each other. This is in the near field. It's fairly good agreement. So if it's so good in the near field, why did we have so many people who died, in Japan? The reason is that in the near field, this is something that we need to have available, faster than real time. The first plot that I showed you in the far field was available pretty much an hour and a half after the event. This was also available an hour and a half after the event. Problem is the tsunami was already there in Japan. So you can do extremely well, but it's after the fact. So one of the challenges that we have is to do, get this same kind of accuracy, but having it in time so that we can warn and evacuate people. Now, and then again, this is more detailed. Even inside narrow bays, etc. This is in Port Angeles. These are simulations of Utkukanoglu. You can get fairly good agreement. So this is the far field problem is solved. And one of the questions here we're going to ask is, if we get all of these details correctly, what is there more to do? And this is where I want to focus a little bit and spend some time discussing what will happen in Fukushima. Because you see, a lot of times in hydrodynamics and in engineering, it's not simply a question of following recipes. I'm going to do this and I'm going to do this. You have to have context in what you do. And if you have if you don't have context, then what you have is what happened in Fukushima. And I'll talk a little bit about my article about Fukushima, which actually was picked up by the national press 2 years ago. It was quite some publicity. I will base it actually not on what I'm going to tell you, but actually on TEPCO's own. TEPCO is the Tokyo Electric Power Company, which was the operator of the Fukushima nuclear power plant. And I will show you the analysis that they do and that they did. And I will ask you, during my talk, your opinion, particularly the students, what do you think they did right or what they did wrong? At the outset, I can tell you that they had designed for a 5.7 meter tsunami in an area that actually only 100 years before, in 1896, it had a 32 meter tsunami. So starting, right off the bat, this was really a wrong, fairly wrong assumption. Then their earthquake size was 7.5, their design earthquake size. And as I said earlier, an earthquake like this happens somewhere in the world, every month or so. And the 6 meter tsunami, they designed for 5.7, we see it somewhere around the world in every 3 years or so. And this is, after all, Japan. But how did they do that? And why did they do that? First of all, let me show you here. This is a map of historic earthquakes around Japan. And you see this is within a radius of 300 kilometers. The reason they put in this radius, the requirements of the International Atomic Energy Agency, is that when you have a nuclear power plant, you consider all the hazards that are within a 300-kilometer radius. So all of this information existed in tsunami catalogs. The reason I'm saying this is that the argument has been made repeatedly about Fukushima. Well, the power plant was designed in the 1960s, and they didn't know any better at the time. They didn't have information. All of these things existed in earthquake catalogs. And to prove it, this is a list from the classic catalog of Soloviev and Go, published in 1974, that is based on about 19 Japanese reports published between 1868 and 1969. As you can see in this catalog, there are several magnitude earthquakes. Of course, these are historic earthquakes. The magnitudes are estimated, but there are at least four earthquakes with magnitudes greater than 7.5. So as far as the argument that TEPCO and the people who designed the power plant back in the 1960s didn't really know about big historic earthquakes, particularly the Jogan earthquake, that's the 1869 event, which was epicenter was very close to the 2011 event. They're not very credible. Then there is the question of what happens. This is what you see when you have good engineering versus substandard engineering. This is the Onagawa nuclear power plant. Give you an idea where the nuclear power plant is. Look at this map. Onagawa was very close. 2011 was about here. Fukushima Daiichi is down here. The distance between Fukushima and Onagawa is about 90 kilometers. So this power plant is almost directly across from where the earthquake epicenter was. And in fact, there was substantial impact. Look at the surrounding area. The power plant comes out fairly unscathed. Why? In Fukushima, which is 90 kilometers down, gets destroyed. The reason is, of course, it all comes to the design. They designed it for a bigger earthquake, magnitude 8.6, 8.3, and they had considered the historic earthquakes, particularly the 1869. So they designed it at a higher elevation. And to give you an idea what difference that makes, this is a table of the 4 Japanese nuclear power plants that were exposed to the tsunami: Onagawa, Fukushima Daiichi, Fukushima Daini, and Tokai Daini. In the first column, what you see is the design tsunami, 13.6. In the column here, you see the actual tsunami height that hit the power plant. Here, you see what the elevation of the power plant was, how many off-site power lines were damaged, and here is the emergency diesel generators. To just expedite things, what really doomed the Fukushima power plant was the fact that they lost all power. So that the earthquake happens, they lose all grid power. The tsunami comes in, they lose the emergency diesel generators, and I will explain why. They're left on battery power. They have emergency batteries. The battery power lasts for about 8 hours. The second unit of the Fukushima Daiichi starts melting down in about the same evening. If you look at this, what can anyone see in this table, particularly here? Tell me what looks strange. Maybe I haven't trained you enough. What looks strange here is that you have power plants that are within 100 kilometers of each other, and yet they have such widely different design heights. Nature doesn't know. You have earthquakes. This is Japan. You have a huge subduction zone. Earthquakes are never repeats of each other. An earthquake historically would have happened here. The next earthquake could happen, anywhere along the subduction zone. You can break one segment of the subduction zone. You can break two. You can break three. You can break four. All this is quite well known. So it doesn't make, even just looking at this, how can you possibly have two nuclear power plants 90 kilometers away from each other, one designed to 13.6 meter design height, the other one at 6. But let's see how they got there. And this is Daini. Daini, by the way, further south, was a very close call. They had built a 6.1 meter, the tsunami was 5.7 meters high. They built a 6.1 meter seawall, which was to protect some pumps. It was completed 2 days before the tsunami arrived, March the 9th. Imagine, we might have had another accident if the seawall had not been there, because the elevation of this plant was small, it was not as high. To start with, what was the problem with Fukushima Daiichi is it started a long time before the actual earthquake. Back in the 60s, the operator, the Tokyo Electric Power Company, they actually graded down the site. Can you imagine? They had a coastal cliff where they would put the plant. It was up here. And they graded it down to build the base of the plant. They could have built it at 30 meters high, but they graded it down to 10 meters. If it had been at 30 meters high, we wouldn't be having this conversation now. But then this was not everything. They had one last chance, and this is where hydrodynamics comes in, to avoid this accident. On the 28th of February 2010, almost to the date, 7 years ago, there was a big, we could say a mega earthquake in Chile, magnitude 8.9, had a tsunami that reached California. It reached also Japan. And on the basis of that, the Japanese nuclear power plant operators, they decided, well, maybe we should do a review of our safety studies. So the operator here, TEPCO, starts a new review of the safety study to see if their power plant is safe. So they feel so confident about the review of their power plant that they go in and present it in a meeting in November. They'll show you their presentation. This is actually the actual TEPCO presentation as it comes down from the web. In the background, I put it there. This will be a lesson how you do these things, or for that matter, how you don't do these things. So what you do is, when you do a tsunami hazard study, you take a source. This rectangle there represents essentially the earthquake source area. It is this S that I was telling you about that we try to, with the scaling relationships, find out approximately what is the size of the rupture area. You take it, you play games with it, you orient it around, you do different things, and then you find out, a hazard curve. If this is your target site, this becomes your design tsunami. Even looking at this, what is wrong here is, and this is, what I was explaining to you earlier, when you have such small distance between them, this is what's referred to as a Class A structure. You cannot pick up, a line that is smaller than, the greatest hazard line that you have over here. So this was a problem, but there is more. So what they do in their hazard study, they study the Chilean tsunami that had just taken place. They had just taken place. And then they do this, they call far-field Chile. This is the way that actually came from the report. It's not my spelling. I didn't change any of that. And they have also a near-field tsunami. Near-field tsunami means a tsunami that takes place offshore, a magnitude 7.5 tsunami. And remarkably, they come in with the same number. If you look at it here, this is about 4.4. This number there is about 4.5. So it's a remarkable coincidence. So you have an earthquake that comes from Chile, that originates in Chile. You have a tsunami that comes from Chile. It arrives in Fukushima. It has 4.5 meters high. Yes, generated by a mega earthquake. Oh, and you have a tsunami just offshore. It also comes out to 4.5 meters, 4.4 to be precise. Amazing. On the basis of that, they don't really wonder about how amazing that is. You add on the, and you can see it here, the maximum water level. You add the 4.4 meters. OP means, it's the reference water level. You add the tide, which is 1.3 meters. You come up with a number that's 4.7. It's out here. So your great elevation of the power plant is about 10 meters. So on the basis of that, you conclude that, famous conclusion, and this is TEPCO's own writing, we assessed and confirmed the safety of the nuclear power plant, only 3 months before the accident. Now, as engineers or scientists, one has to be very careful when you publish things and you say, we assessed and confirmed. Confirmed is a very, very strong word to use. And that's not good at all. So this is what they did. What is also wrong here? Maybe, none of you, and we're not, none of us is into actual design. But another thing that's wrong here, and if you were in a more, I also graduated from a very theoretical school, you would know about such things as safety factors. You come in with an estimate that's like 6 meters. If you have a safety factor, you say, well, this is a nuclear power plant. I will double it to make sure that I am okay. So they come up with 5.7, and it becomes 5.7. Okay, doesn't matter. My level is at 10 meters, so I'm okay. I'm okay. Well, they were not. So to finish this discussion with Fukushima, so I can go into more interesting fluid phenomena, as I said earlier, what doomed it is the emergency diesel generators. An amazing feature of this power plant, but if you see what happened here in Hurricane Sandy in New York, where in hospitals that flooded, the emergency diesel generators were in the basement, they had actually located the emergency diesel generators in a basement. So they were so certain that they would never get a tsunami, but this is Japan. The very word tsunami is Japanese. You have the emergency diesel generators in the basement. So once the tsunami, the power plant was not damaged by the earthquake. It was not damaged structurally per se by the tsunami, other than minor damage. But the main damage was because you didn't have electric power. They site them in the basement. Government reports, by the way, are mysteriously silent on this. It was very difficult to find out exactly where the emergency diesel generators were, but they were in the basement. Most of them, for units 1 and 6. So such siting of a nuclear power plant, of course, is incomprehensible. That's the only best word that I can use. Now, last detail here. I was telling you about, and this is where I made the introduction about Ambraces and Reichlen thing about the worst case scenario. What was also wrong with the TEPCO analysis? You have an earthquake that just happened. You go in and you try to model an earthquake from Chile, but you only model one, and you model one local tsunami. What should you have done instead? You should have modeled earthquakes all along the Pacific Rim, all along here, areas that could generate earthquakes, and on the basis of that, estimate what is the impact in your target site in Fukushima. So this is the lines here are proportional. All these are unit earthquakes. In essence, they're normalized. They give you, the relative height in Fukushima. The main thing here is that for the earthquake that they checked, this is what the result that they got. But if they had moved the earthquake a little bit further down, they would have gotten almost twice the height. If they had used an earthquake in the Magnus subduction zone, they would have gotten much higher. If they had used an earthquake in the Japan Kuriles further up here, they would have gotten a higher tsunami. If they had used an earthquake in the Alaskan Aleutians or in Cascadia, they would have gotten a height that would have been twice. So even for their scenario, if they had done what we've been doing, starting from Burak Uslu, one of my students, in the 2005, 2006, this was actually done by Nika Ligeris. This is a hazard analysis that you do. You consider all possible events, and out of all the possible events from everywhere, you actually pick up the worst. Instead of doing what they did, which is arbitrarily you decide that my worst possible scenario comes from Chile, and it's this particular earthquake, and then my worst possible scenario locally is a 7.5, so I pick that up, and I come out and I do it. This is what I'm saying about doing things out of context. I mean, if you look at what TEPCO did, they had a really high-class code. I mean, they had fantastic resolution. I mean, they talk in their reports about what all the special effects they did. But unless you have context, what does this mean? I mean, if you don't have the right initial condition, you know, it's totally meaningless to pay a lot of attention in the details of your computation. So, moving on, and these are some of the conclusions. I don't want to spend too much time to show it to you, but I'll tell you the law of unintended consequences. Of course, because TEPCO had thought about 7.5 earthquake as the initial condition, they used the same scenario to develop inundation maps or evacuation maps for the area. This is a school in the Sendai Plain. This school was outside the inundation zone, which means outside the evacuation zone that they had planned for. So when the earthquake happens, the students in the school are trained, strong ground shaking, evacuate, go to the outside the building. They hear the tsunami warning. What do? It's outside the evacuation zone. They are not supposed to do anything because their school is outside the evacuation zone. So, well, they decide, to be cautious, and they move back to the second floor of the school. Aftershocks. Oh no. Now there starts an argument between the teachers. All of this in Japan, where some of the best prepared people in the world. And they argue among themselves, so what do? Do we move down because the school could be structurally damaged? In the meantime, they keep hearing the tsunami siren. So what happens? About half of the people, half of the teachers, half of the students, take students and they go in and wait outside. Half of the people wait on the second floor. These are the belongings of the people, of the students who actually evacuated from the earthquake, and they went out. And only if they had moved up to this level, up to the balcony, they would have been safe. So having the wrong initial condition didn't just affect Fukushima, it affected everyone living along the Sendai Plain. So what would have been useful? How would these people would have been saved? One idea that I've thought about a lot is coming up. For now, we have an evacuation zone. We say, well, this is the limit of the evacuation zone. But this is not enough. What we need is something analogous to what we have in hydrology, which is the hydrograph. And the hydrograph gives us some idea of how quickly the water depth will change at any given location. So I'll show you some of the steps that we've taken to do. And one of the hardest things, by the way, in tsunamis, in when you do field measurements, usually we locate the maximum level that the wave reaches up to, and we call that the maximum run-up. But it'll be nice to know how quickly that happens, how quickly we reach to the maximum. So we need to have some idea of the velocity of the tsunami on dry land and how quickly the depth changes. We started this, and I'll show you some measurements from Banda Aceh. Then I'll show you Japan. Whoops.
Dan tanpa ini warga mulai berlarian karena gelombang tsunami mulai datang mengejar mereka. Mereka lari menuju ke arah Masjid Baitur Rahman, di mana di sana juga ada Wahid dan Munawar yang mengabadikan peristiwa ini. Mereka berada di tempat wudhu, pengambilan wudhu di Masjid Baitur Rahman. Gelombang
When you see things like this, it turns out that the flow becomes supercritical. In the these are called, rooster tails. So within about, does anyone has a quick estimate how quickly the flow turns from this slow flow in the beginning to this? Supercritical? Huh?
Half a minute to a minute.
No, less. Huh? 30 seconds. In the 5 minutes, keep on. You have the right answer for Japan, not for this. Half a minute is right. So what we did is with my colleagues, with Jose Borrero, and this is Herman Fritz, we went there. We tried to orthorectify the images. We had access to this video. We tried to find the place that the video was shot. This is the location of a different video. We did this, found the place, orthorectified the images, which is a time-consuming process, but it's fairly standard. You try to sort of change it. The final image looks something like this. Find out the velocities, and what you find out is that the velocity is about 2 meters per second, and within about 30 seconds, it almost goes to twice the value. And this is part of the reason why tsunami floods are so counterintuitive. I mean, with a very short period of time, and just change, the speed can increase very, very rapidly. And what you see here is the same data, v as a function of the wave of the flow depth. And this is only just to show that at this location here, the flow starts becoming supercritical, and then again it's subcritical. So this is for Aceh. We try to do this for Japan, and for Japan we have more videos, more data. So I will show you something more complete. This was what I showed you, a result that we got back in 2006. Let's see how well we did a few years later, or 6 years later. This is Kesamula. In Japan, one of the problems, you see the science that I'm telling you in the school. One of the problems that we have is you see something like this. How can you extract quantitative data? Well, of course, if you know the size of the buildings, where they are, all of this, if you have a fairly accurate map, you can orthorectify the image. You see something. Look at this building there. Our sort of reference. Based on that, again, we went through the process of orthorectifying the images. Hermann Fritz went back after me and did actually a LiDAR of the entire area, so we would know all the distances, etc., and to be able to interpret the video that you saw. This is the building that you saw again. This is where it was shot from. So this is, in essence, where I will present to you the hydrograph. So if you do all this, which is fairly straightforward conceptually, but very, very, very time-consuming in terms of implementation, you get this, bingo, the first ever tsunami hydrograph. What this shows is how quickly, in this location, the water depth changed. And if you look at this thing here, look, at around 1525, 0, this is essentially the leading depression of the tsunami, but this refers to what happens just offshore. 1525, the depth is 0. At time 1535, within 10 minutes, in fact 9 minutes, how big is the depth? 9 meters. So you have a change in depth of the order of 9 meters in 9 minutes. So about 1 meter per minute. That's how quickly it changes. So this is the kind of information that we're advocating very hard that warning centers and local civil defense should distribute in the various evacuation shelters so that people know, or schools, etc., so that people know, if the worst possible scenario happens, how quickly are they going to flood, how much time they will have. So this is something that is in the process of at least being thought about, developing tsunami hydrographs and going beyond just giving the maximum penetration line. Now, I said earlier, one of the things that I was looking at, and there were 2 more things that I will talk to you about, is why sometimes the tsunami appears, the first wave is the largest, sometimes the second. We're not going to go to the third one. And we're going to look at the propagation along great circles, and this is the Japan tsunami. But to start and to try to understand this, at first we started with a fairly simple model of essentially a dipole wave. Earthquake deformation of the seafloor is, you have a region of uplift and a region of subsidence, and you have a wave that looks like a dipole with a finite crest length. It looks something like this. This is very much like the initial wave, of an earthquake. See the dipole? Now, the way that this dipole propagates, this side propagates, and I'll show you an animation, towards the coast. This side goes towards the deep. What would you expect? When you see something like this, the intuitive part that most people would expect is that this side that propagates here, where the elevation wave is, this is where you're going to have the highest wave. It turns out, if you look at over the whole computation, what takes place, the maximum is on the side of the depression wave. This is here is the initial wave height. Remember, this over the whole computation. I will show you this in animation here. Totally counterintuitive. So it turns out, I mean, this is all linear theory, but it turns out that if we use linear non-dispersive theory, linear dispersive theory, nonlinear theory, nonlinear non-dispersive, you have very similar results, which means the maximum is on the side of the depression as the wave. Okay, this doesn't tell us much. This tells us that, you expect, on the other hand, the way that the wave propagates, the depression wave propagates towards the shore, the elevation wave propagates offshore, doesn't really give us a lot of information about the wave propagating offshore. But this does. If you look at what happens as the wave propagates along a great circle. This is exactly the same wave. This is on a treadmill, so that it stays on the same place. This is the wave propagating along the great circle. What you may not have seen, and I'll start again, the wave starts. Look at the wave. See the exchange between the first and the second wave. This is the leading wave in the wave train. The leading wave becomes smaller. The same thing flipped around on, as I said, on this treadmill. So we try to understand when this happens. And to do that, first of all, we looked at measurements from different bottom pressure recorders that I was telling you about that we use for inversion. These are across the Pacific. And this record we call maximum first when the first wave is the maximum, maximum delayed when the second or the third wave is the maximum. And it looks like, there's no consistent pattern. So we try to understand that. And to do this, you need to have a fairly simple model. And our model was as simple as it gets, essentially a pillbox, generate a cylindrical wave. And what you have from this cylindrical wave, you have very close to the source, you have something that looks like this. This is maximum first. Far from the source, you have maximum delayed. You can see here the second wave is the highest. Now, the interesting question is, what is the critical distance that this transition takes place? And on the basis, by the way, the second waves, they're both dispersive, and here we plot especially a spectrogram, this work that done with my colleague Emil Okal. I tried to find out a simple analytical expression for the transition distance. I couldn't, but then we ran hundreds of experiments based with an analytical formula, and then we figured out where the transition distance was, and we did a linear regression. And then what got my attention is that the coefficients here, this is 3 and this is 2, which means these are the logs that this transition distance was going to depend on the third power of the size of the source and inversely proportional to the second power of the depth. So this gave me a little bit more confidence to search for some kind of a scaling argument. And in fact, I don't want to go to the details. It's too late in the day, and I might get in trouble with Professor May. So, but I think it's robust. We come up with a scaling argument that, sure enough, this is to the third power, and this is to the second. So, in essence, what this says is that, for far field propagation, you are going to have, the maximum is going to be delayed. You can see it here fairly clearly. Very close, you're going to have the maximum first. At larger distances, you're going to have the maximum delayed. So we think that we're on the right track there to try to solve this problem. Another problem that they don't want to, we have many of these. Another interesting problem, and this is what I will end up with, I promise in less than 5 minutes, that we had in Japan. This was the fact that, there's this photograph from Urai in northern Japan, and you see during the flood a fairly large vortex, or if you will, a turbulent coherent structure. This is here. What does this area look like? If you look at this, this is the same one as this, and here is to a larger scale. This feature is this feature here. Notice this breakwater there. So this is large vortex that's generated, obviously persists there for quite a while, and then photographs of it. This is in the near field. Far field, or in Guam, which is southeast of Japan. This is a U.S. naval base. What you see here is this is where a submarine base was. This is the outer basin, the inner basin. Two nuclear submarines that were anchored here and there broke off their moorings. What you see here, this window, is this window over here. And they started wandering around. The weird thing was that, as opposed to Japan, that you had a really large wave, here in Guam, the height of the wave was only about 40 centimeters. So you have a really small tsunami, and yet it generates such a strong current that the moorings break. As it turns out, we think also here there was a large vortex. This is not the first time that this is observed, but it's the first time that actually we realize exactly what went on. In the Indian Ocean tsunami, in 3 far-field ports from Sumatra, remember this is the origin of the 2004 tsunami, in Reunion in Madagascar, a couple of hours after the arrival of the main wave, there are big waves that form, and ships break their moorings, and this is part of the work that was actually done at MIT. 50 years ago, which has to do with harbor resonance. I mean, late on in the wave train, you have the first tsunami arrival. A couple of hours later, you have the slower, shorter waves coming in that are capable of exciting the harbor, so you start getting harbor excitations. And my colleague, Emilio Cal, actually did some back-of-the-envelope calculations and figured that this was happening. But Salalah was different. Salalah is in Oman, and it is the 16th largest transshipment terminal in the world. This is the port of Salalah. This is the same as that. This is the drawing of the harbor master, what happened that day. The Merck Mandraki, that's a 286-meter ship, was right there. Here it was being unloaded, and then it broke its moorings. And according to the harbor master, who actually made this drawing for us, again, I'm trying to get the cursor. Well, I'll use my hands. The Merck broke off here, started going around in circles, went out this way, and ended up on a bar. In the meantime, another ship that was there couldn't come in, was waiting for the currents to come down. And at the time, we really didn't evaluate this, the way that we should. But in the light of what we saw in Japan with the vortex, etc., we understood that what happened there must have been, and in fact, the drawing tells the whole story. Some sort of, and the drawing was done, as I said, by the harbor master back in 2000 when we were there in Oman. I was there in the summer of 2005. So a whole series of experiments starts, and I will show you here. This is work of partly Ned, but primarily of our student, Nikos Kaligeris, who's one of the most exceptional students we've ever had. This is in the Oregon wave basin. You have the wave generator coming in this way, and Heidi, you were right. I was wrong in the morning. I mean, you had a very good sense about which way the wave goes, and I'll show you the particles. This is particle tracking par excellence. And you can see here the vortex being formed as the wave comes in this way, and then gets reflected and goes out. There is a lot of work that goes in to generate this. And the work of Nikos Kaligeris is basically to go in and find out what is the vorticity, try to understand the large-scale structures and the way that they behave. But we had an opportunity to actually observe this in the field. About a year and a half ago, there was a tsunami warning in California. There was a big earthquake in Chile, another one. And this, there was a tsunami warning at 6:45 p.m. We knew about the tsunami from about 5 o'clock. And Nikos went out and did we have the capacity of doing a very quick model of the earthquake, and we tried to figure out in which of the local ports in California there might be strong currents, to go there and try to see if we can observe in the field what Nikos was actually observing in the laboratory. It turns out this is Ventura Harbor. Ventura is about 100 miles north of Los Angeles, that it looked like there would be strong currents. So right then, that night, the whole tsunami group went into hyper gear. as we usually do when there is a tsunami that takes place. And, but now beyond just modeling, what we did is we tried to go out and buy every GPS logger that we could find on hiking stores. These GPS loggers actually transmit data, some of them every 2 minutes, some of them every 2 seconds, so that we could make GPS floats, go in, leave them in the port, and then hope that as this tsunami comes in, we would get some traces of the tsunami, and at the same time try to get do optical analysis, just like Nikos did in Oregon. So that we had spheres like this to create particle trackings. We had the GPS floats, and we had the camera. And you will see the results. First of all, what does it look like? The camera was only useful after sunrise. The tsunami came in at around 5:05 or so. This is a time-lapse shot. You can believe it or not, and I'll show you what this looks like. All of this is data. And all of this we can interpret. And actually, I'll take it, I'll turn it upside down, and show you what the flow looks like. The port was not closed, so you see ships coming in and out. So we have two kinds of data from Ventura. We have the data from the GPS trackers, but we also have the optical data. And one question is, how good are the optical data? By the way, these are the tracks that we got from the GPS trackers and also from the floats we had, which is much more difficult than it sounds because you get in, as the tsunami comes in and out, remember, it's not a single wave, you get the tracker that gets stuck into different places, so you have to go in, unstuck it, people have to go into the water, etc., throw it back in, do all this stuff. But the interesting thing is that the optical method that we use, and I'll show you, when compared for the same locations with the GPS trackers, optically we can determine the velocity fairly well. Again, this work, you see something like here that looks very nice, etc., but that particular plot is about a month's worth of work. Just here on the right. So then the next question is, how well can we model this? This is the data from the GPS tracker. And if you look, how do you do, when you have different tracks here, how do you compare it with predictions? One of the things that we did is we tried to sort of separate in different parts of the flow. And to make a long story short, what you see here is the comparison of the GPS tracks with the results that we get from our computer code from most, and again, the results are satisfactory. Now, I spoke about vortices, so what does the flow look like? I spoke about doing optical tracking and Nikos being able to actually obtain velocity data for the entire flow. So look what happens once you do optical tracking. Again, this is the Ventura, and look at the flow. You can see the large-scale structures that are formed, that are shed, how the flow reverses, goes in and out. Remember, the tsunami here is of the order of about 50 centimeters or so. It's a very, very small tsunami. And yet, fairly interesting special effects. The currents are fairly strong, by the way. I was there in that morning on the harbor master's boat, and he sat to the engines, and we're there, and sure enough, when the tsunami arrival was there, we felt slowly turning. He asked me, in fact, are you sure we can do this? And I said, no problem, it's my code, I know what I'm doing. So we were actually there when the tsunami came. So I try to take you through different challenges that we have in hydrodynamics and where we think we stand. And I think the take-home message is that we are at the point that we can have real-time predictions. We can assimilate data that comes in from buoys. And this really helps us sort of fill in the gap, because the seismic information alone cannot really help us solve the problem. But then in the process, we find out that there are many, many different special effects that we need to pay more attention. Turbulent coherent structures is one of them. We would have never thought that a small tsunami can have such impact as we saw in Guam or over here. And when we think about the worst, and this is my last slide, in terms of thinking of the worst, please remember that we exist because the dinosaurs don't. And what I mean to say by that, the dinosaurs obviously were created. They were destroyed by a huge natural disaster. I mean, this is the Chicxulub impact. So I do not advocate, when you think about the worst, about looking at Chicxulub-like events, but nonetheless, if you want to avoid Fukushima-like disasters, you really need to consider all possible scenarios and details, which of course is fairly hard to do, but this is what makes our work so interesting. Thank you so much.
So you mentioned at the beginning of the talk about how sheltering islands can sometimes intensify the tsunami.
Yes.
Can you give some examples of that?
Absolutely. I don't have it here. You see, the old-fashioned way. What happens here is you have an island. The shoreline is over here. You have a wave that's coming in. Now, as the wave comes in, it kind of wraps around the island. In fact, this is something that we had seen in Flores in 1992, that we have an enhanced run-up on the back, but we never put a shoreline here to see what happens. As the wave runs around, roughly speaking, these things turn. These two waves turn in. What you have at this location, you are going to have higher run-up than you do over here. And this we noticed, this is why it is so important to go out on the field. This is in 2010. This is the Mentawai tsunamis in Sumatra. That I went there. This is the Mentawais, that is islands off Sumatra. And off the Mentawais, there are small islands. And it turns out that wherever the island is, there is actually a fishing community, because people go there because they have the mistaken belief, even though the islands are far away, that somehow from the wind, etc., the waves, they're going to be protected. So, and lo and behold, a lot of the communities in the Mentawais have islands fronting them. And it turns out that in those communities we had the most damage. And I kept seeing this, and I thought, this is weird. I mean, this place, and you go in a few miles away, and you don't see the same damage. I mean, what is wrong? I mean, why did they build the village in the wrong place? They build in the wrong place, again, because they think that they're going to get protection. But if you think about this, the amazing thing, by the way, because we've done quite a bit, I had a PhD student do work on it, I mean, with machine learning, and try to do all possible combinations. Under no circumstances does the island offer protection. At best, I mean, if the island's far away, you're going to have, essentially, the island is not going to play any role in the run-up. If the island is close enough, then the island invariably will enhance the run-up behind it. And then we have, right now, we're doing experiments at OSU, because that's so unbelievable that I convinced NSF that was something, don't trust machine learning. Let's actually do a physical experiment and see if this is true. And it turns out in all the experiments that we've done to date, this is the case. And we observe it in the lab, we observe it numerically, we observe it on the field. So it is real. Hope.
Was TEPCO the operator for the 4 nuclear plants in the Fukushima
good question, sir.
proximity?
No, it was a very, very good question. TEPCO was the operator only for Fukushima Daiichi and Fukushima Daini. I'm not sure if they did the Tokai in the south. No, I'm not sure. Certainly, they were not the operator for the Onagawa. Onagawa was a different company called Tohoku Electric Power Company. Also, you can think about the initials are TEPCO. TEPCO is the Tokyo Electric Power Company. So it's a different operator. This is why they had this much more cautious way of going about this. I mean, they had, they looked into what was the worst scenario, what had happened in the area. The amazing thing with, TEPCO was the fact that in the beginning, they were in denial in terms of the initial condition. They said, we didn't know about this tsunami had hit the area. But somehow, the other electric power company knew about this, but TEPCO didn't. It was really substandard engineering. And it's not only, and I mentioned this two-pronged approach. It was not just the initial condition for the near-field tsunami. You can say there, for whatever reason, it stuck to their minds that you had a 7.5 earthquake. What about far field? I mean, the far field, the hazard from the far field, you need to have scenarios from everywhere in the Pacific, and this is standard hazard analysis. that we do. You cannot take one far-field earthquake in Chile, because what happened is that all this is triggered because a wave comes in from Chile. It could have come from Alaska. Okay, then you would have done a different analysis for Alaska. So I don't want to say it, but yes, I mean, it was really substandard engineering.
Strange that the authorities allowed the 4 nuclear plants in the Fukushima proximity to be designed to withstand different size earthquakes.
Yep, it is.
Weird.
Well, it is amazing, but I mean, this is one of the conclusions that I had, and I didn't go through much to it. There were substantial deficiencies in Japan's nuclear regulatory structure. Incidentally, the best report that there is of the Diet of Japan. The Diet of Japan is the Parliament of Japan, who made a scathing report pointing some of these things out, and particularly blaming this on a culture of how insular the regulatory agencies were in Japan, that they thought that, they were, I wouldn't say above it all, but obviously they were very introverted. They didn't go actively seeking information about their plans, and I mean, this is the consequences. Onagawa is something that I discovered on my own, because as I was looking at this, it was, I mean, amazing, because it's just directly across, and how come this plant was not hit? But you see, had this been in any different place in the US or in Europe or other places in the world, people would have been, there would have been litigation, to say the least, prosecutions about this. I mean, how come you did this? But Japan is a different kind of a place. I mean, this is something that was handled in a very different way.
Quite familiar with the New Yorker article about the major anticipated earthquake off the northwest coast,
Yes.
and the fact that in Japan, in an event, there was evidence of a similar event 300 years earlier or so, and that there are stone monuments at the high ridges on the coast that had been mossed over, I guess, and forgotten. What are the implications of that for the rest of the Pacific Rim, if that were to happen, and what's the implication along the coast of the United States?
It depends. Again, as a community, we tend to, repeat or do Fukushima-like mistakes. For example, in the Pacific Northwest, there are 4 different scenarios for this large earthquake. The event you're referring to is the 1700 earthquake, which was highly controversial in the 90s. People fought it to death. People thought that, maybe Cascadia, because it has not produced any earthquakes recently, there was some evidence of large earthquakes. This was the work of Brian Atwater. He was a sedimentologist, had found these large earthquakes in Cascadia. Again, for things that have happened hundreds of years ago, how do you determine the earthquake size, etc.? So people thought, no, these are not magnitude 9. These are not what we tend to call megathrusts, earthquakes at magnitude 9 and above. These are not megathrusts. Maybe they're magnitude 8.5 earthquakes. What's the impact of them? Well, it turned out that there was evidence in Japan of an earthquake, of an orphan tsunami in 1700. Orphan tsunami in Japan, there are extremely good records for the last 800 years of earthquakes and tsunamis. There's this earthquake, there's this tsunami that's not associated with an earthquake. And it so happens that in the US, we have a fairly good idea about when the earthquake happened. It's from Indian legends. The dates fit extremely well. The modeling fits. So that helped clinch the idea that Cascadia can generate fairly large tsunamis. But now, of course, if you are, and this is part of the problem that the practicing engineers go through, why are there 4 scenarios for Cascadia? Because people have existing facilities that are at different elevations. And if you use a magnitude 9 event, maybe your facility doesn't get flooded. But if you use a magnitude 9.2, it does get flooded. Or if you use a magnitude 9.4. So the Oregon DOGAMI, which is the Department of Oregon in Oregon of Mines and Geology, has a medium, large, and extra large scenario. And depending on whom you know, and I'm not being facetious here, in the legislature, they let you get away designing it with the extra large or the large or the medium scenario. But to answer your question, the implications across the Pacific depends where you are. Obviously, it will have impact in Japan, and given the technology that NOAA has, I think there will be ample warning in time. For example, for a tsunami to come from Japan to the US, it's 14, 15 hours, 16 hours. From Chile to Japan, close to 20, 22 hours. So for this far-field earthquake, for these far-field events, we have enough time to have really good warnings. The problem is what's going to happen in Cascadia. For example, Seattle is going to get a warning of the order of less than 30 minutes. Some people say, depending on the location, less than 20 minutes. Can you evacuate Seattle in less than 20 minutes? Well, yes and no, because someplace in Seattle you can do vertical evacuation, downtown Seattle, what happens in the lakes, etc. All of this thing is the right people who are handling this. And then there are all the communities along the Oregon coast, and they have inundation maps, etc. They do a lot of training so that even if you get a warning and you have only 5 minutes to get to safety, you can get everybody out in a fairly short period of time. I think the standard that we're working on right now as a community is to have a warning for Cascadia in less than 10 minutes after the earthquake starts, which means, a mega thrust like a 9.2 is going to shaking will last about maybe 6 minutes. So 6 minutes after the shaking, you would get, pretty much 4 minutes later, you would have a warning. Of course, if the earthquake, all of this is highly theoretical. The main message is, if you are close to the coast, like for example, if you live there, and this is what most residents in the Pacific Northwest know, and you feel the ground shake, do not worry for sirens or anything like this. If the shaking lasts for over 30 seconds, this means that the earthquake is at least a magnitude 7. You evacuate to high ground. Because if you are to wait for the warning centers to go through the procedures, do the data simulation, NOAA run the codes, etc., and you get a warning in 10 minutes' time, that's 10 minutes later. If you wait 30 seconds, so a lot of communities have that, and they know that if the shaking lasts more than 30 seconds, you self-evacuate. You go to the evacuation centers, you move to high ground right away, and you don't wait. And in fact, my experience for spending quite some time in Japan is in places like Kesenuma, where I did this video, where I spent quite some time. I talked to the emergency manager. In Kesenuma, proportionally less people died in the flooded zone than in other places, because the gentleman actually pressed the siren the moment the earthquake started. He didn't wait. Somehow he knew that this was going to be a big event. Don't ask me how. Maybe he waited. He told us right away, even if he waited for a minute. But this gave everybody a head start. He started evacuating the city before even the earthquake shaking had stopped. So for near-field events, this is the way to go. I'm afraid it's going to take us quite some time to get to the point that we have for near-field events, such good and robust technology that we can afford to wait until the earthquake stops and then, decide, if we want to evacuate or not. This is true anywhere you are in the world. Anywhere you are in the world, if you are close to the coast or near the beach and you feel the ground shake for more than 30 seconds, evacuate.
I have a more physics question.
Sure.
Is there any special counterintuitive physics involved in explaining why an earthquake in Chile can propagate to Japan and still generate a really large wave?
That's the way. Yes, there is a physical explanation. If you have a rupture, it's over a certain length, the waves are going to propagate. The primary directivity of the wave is perpendicular to the rupture. And because tsunamis are such long waves, they propagate with fairly little dissipation across the ocean. So it is a very efficient, and we talked as a community, and C.C. May and Olli Madsen did the key experiments back in the 60s about finding out, how solitary waves propagate, the transition over the continental shelf, how they're efficient, etc. Even real tsunamis, which sometimes, they're not solitary wave-like, they pack energy fairly efficiently, so they can propagate very large distances. And exactly because there is a primary directivity in the direction, there is of course there is three-dimensional spreading. That's why you have the waves that can start from Chile and go to Japan, and vice versa, from Japan to come to California, or from the Aleutian Islands. You remember the first slide that I showed, 1946? That's the Aleutian Islands, Alaska. It goes all the way to Hawaii, then French Polynesia in the South Pacific, all the way to Antarctica. Starts from Alaska, goes to Antarctica. A wave generated by 7.5 earthquake, sneaking.
All right, so we can continue if you have more questions, but we let everybody else go. Please join me in thanking the speaker, and thank you for all coming here today.
You're very welcome.